Welcome everyone. Today's seminar is titled 24-volt plus power supply solutions. And in this section, we are going to take a look at products that are optimized for the 24-volt bus. If you recollect, Bob spoke about the evolution of power supply solutions. He described how the first circuit blocks were integrated to make controllers, and then how the MOSFETs were integrated as well. Let us call these devices integrated FET switching regulators. And then more recently, we have integration of the inductor to make power modules. So that makes three types of solutions, or design approaches if you will: controllers, integrated FET regulators, and power modules. All three types of solutions have their place in a typical power application due to their specific advantages. For this talk, we will focus on integrated FET switching regulators. Synchronous rectification is not new by any means. It has been around for a long time at the 12-volt and 5-volt supply voltage levels in the mobility and server applications, and has really helped leverage the benefits of efficiency and low temperature rise that Bob described in his section. However, synchronous rectification for 24-volt bus application with 60-volt operational capability is a relatively new development. We see such devices proliferating in this space over the last 4 to 5 years. There are strong design challenges to be overcome here, and Maxim has successfully solved these to develop the broadest range of such products in the market. Here is an example device, the Max 17503. It is a 4.5 to 60 volt input, 2.5 amp synchronous buck regulator. The 60 volt rating is not chosen by accident. It is based on feedback from several customers that the single biggest reason for field failures is lack of voltage rating margin. For robust operation in an electrically noisy environment, voltage rating margin is critical. TVS devices placed in the front end are not good enough to protect the downstream devices if your real-world surge has enough energy to raise the TVS clamp voltage high enough. The Max 17503 uses peak current mode control. Bob explained this and described how this makes for a simpler compensation scheme and has inherent current limiting. These features make current mode control an excellent choice for integration. By the way, the schematic I'm showing here is pretty close to the complete schematic you need in order to implement a working regulator. The main goal for these family of products, we call them Himalaya series, is ease of use or easy implementation. We want to make it very easy for you to get first pass design that works. The product definition and design shoots for this. Back to the current limiting. You can see that there are no current sense resistors needed to sense current and no differential traces to run on the board with sensitive current information. We sense the current on the internal high side FET and convert this to a ground reference signal and use this for both control and current limiting. This makes for a very clean schematic and easy implementation of the power supply. The loop compensation is also integrated, and you do not have to deal with the design of these components. The feedback resistors interact with the internal poles and zeros to take care of this. We will look at more details on this when we go into the design details. The enable or EN and UVLO or undervoltage lockout pins can either be used as an enable pin or as a UVLO pin that can be used to set the voltage at which the regulator will start up. The RT pin allows setting the switching frequency, which is the main optimization driver for an internal FET regulator, as it enables trade-off between efficiency and solution size. It has a default 500 kHz switching frequency setting. External clock synchronization is available for situations where there are multiple devices in that design that need to be synchronized to a common clock in order to avoid low frequency beat on the input bus. The mode pin allows setting of the preferred method of handling light load efficiency, either CCM, continuous conduction mode, DCM, discontinuous conduction mode, or PFM, pulse frequency modulation mode, can be programmed. Bob explained this in his section. At light load, the capacitive losses of the device dominate, and these are frequency dependent. In PFM mode, We push more energy to the output than is required by the output, thus causing the control circuit to skip pulses. In other words, reducing the effective switching frequency and hence reducing the frequency-dependent capacitive losses and improving efficiency. In DCM mode, the part inhibits negative current flow and improves efficiency marginally at light loads. In the CCM mode, the part operates at constant frequency at all loads and features the lowest light load efficiency but the best ripple performance. SS, or soft start, implements a soft start to limit the inrush current from the input supply. The soft start time can be programmed by adjusting the soft start capacitor. Regardless of mode pin setting, the device starts in DCM mode, thereby inhibiting negative current. This allows startup into pre-bias output capacitors. When the soft start is completed, the device transitions to the selected mode, i.e. either DCM, PFM, or CCM. Reset is a power good signal that goes high when the output is in regulation. The device also features internal N MOSFETs, or NMOS, for both high side and low side and delivers a peak efficiency of 92%. Here is how the device is laid out on our standard EV kit or evaluation board. As Bob explained, you can see how the power stage components are all on one side, the input capacitor, the output capacitor, and the current control components are on the other side. Integration in this way forces the PCB layout to follow the pinout and helps avoid the layout mistakes that would otherwise occur in controller-style designs. We also provide ready-made Gerbers on our website for you to use as easy reference. The signal ground, or GND, and power ground pins are right next to each other, making it easy to implement a signal point or star grounding scheme. Let's now look at a design example and get you introduced to Maxim's EESIM tool. We will use the tool to show you how to design for the key aspects of thermal as well as loop stability. The tool uses the simplest simulation engine. Let's look at the detailed specification of an example design. In this case, the minimum input voltage is 6.5 volts, the nominal input voltage is 24 volts, maximum input voltage is rated or specified to 32 volts. The undervoltage lockout, or the rising undervoltage lockout, has been set at 5.5 volts. The output voltage has been configured to 5 volts, and the output load has been set to 2 amps. The input capacitor ripple is set to 1% or 240 millivolts. The output voltage deviation for 50% load step is desired to be 3% of Vout or 150 millivolts, and the max ambient is specified at 85 degrees C. Specifying your maximum operating ambient temperature is critical since this helps the tool recommend the right design. We will review this in more detail further along in the talk. The tool can be launched from the device page on the Maxim side, as you can see highlighted in the red circle. The tool allows you to do trade-offs between size and efficiency, the main driver here being the choice of switching frequency. Your smallest solution is your thermally limited design. You cannot have a design that runs the junction temperature higher than 125 degrees C at the maximum ambient temperature. Your most efficient design is with the lowest switching frequency. The balanced design, as indicated on the slide, falls somewhere in the middle and is a design that uses the average of these two limiting switching frequencies. There is also a cost versus performance trade-off that the tool allows you to pick from. When the tool picks the parts from the database, it selects components that fit the allowable range specified for the component. For example, inductors in the range of 8 to 12 millihenry will be picked for a nominal 10 millihenry requirement if cost is chosen. The tool picks the lowest cost part in this case. If performance is chosen, it picks the lowest DCR inductor. Okay, let's look at the design criteria next. We have here chosen a balanced efficiency design. The customer has the ability to select the mode of operation between PWM, PFM, or DCM. The customer also has the ability to select or pre-program the soft start time, which in this case we have chosen to be 3 milliseconds, and also specify the maximum ambient operating temperature, which is 85 degrees C. You will notice here that the switching frequency defaults to 330 kHz in this case, depending on the other design criteria entered by the user. The tool also has the ability to flag a wrong choice of switching frequency if it violates the thermal requirement. In this case, we entered 500 kHz, which is clearly outside of the allowable range, and hence the simulation model is smart enough to flag it to the user. Now, we hit Create Design. Well, as soon as you do that, the schematic shows up. There are several features here, but let us focus on the main ones: recalculation and simulation. Recalculation allows redesigning the schematic after making changes to it, and the Simulation tab allows launching several simulations. We will get into the details on subsequent slides. You can play with the schematic based on your specific needs. For example, the tool chose a 3 times 10 microfarad for output capacitors. Let us say I want to change it to 2 times 22 microfarad, 1206 case size. I can double-click the component and change it as highlighted on the screen. When I double-click, this dialog shows up. I can go into the View or Change Vendor part and pick another option. There is also a custom option to put in your own part if needed. The lock icon allows you to lock the component of your choice so that the tool does not change it during recalculation. Just to showcase what the database looks like, this allows you to select the components from here that suit your design. In this case, we have chosen a Murata capacitor, which is a 22 microfarad capacitor. Okay, now we have locked the component that we changed. We hit Apply. The new details show up in the Properties section. Closing the dialog box, we go back to the schematic, and the component shows up as half yellow and half green. This means that you have chosen to not change this during recalculation. Go ahead and hit the Recalculation tab. The new schematic shows up. No changes from the old schematic since the output capacitance is the same range as the earlier design. Okay, let's take a brief look at the Simulation tab. The Simulation tab has various aspects to it. First, you'll see the load step. Secondly, the AC loop or the Bode plot analysis, steady state analysis, line transient, startup analysis, as well as efficiency analysis. These tabs are listed on the right of your screen as highlighted on the slide. We are now ready to look at the thermal performance of our design. For this, we use the efficiency simulation. Note that the worst case analysis should be done here. So we should plug in the maximum DC input voltage for this simulation, which based on our previous requirements or specifications was highlighted as 32 volts. Hit Run Simulations, and once done, the efficiency text in the View Waveforms lights up on the right of your screen. Clicking on the efficiency text shows the efficiency graph. This is the worst case efficiency at the maximum ambient temperature and includes process variation. In essence, this is the lowest efficiency that you can expect for your design given process corners as well as temperature variation. We are highlighting a peak efficiency of 89% for the specified design and a worst case full load efficiency of 87.5%. You also get a junction temperature graph that assumes the theta JA specified in the datasheet. This is a reasonable assumption that is also validated on our eval boards. Theta JA is a strong function of board design. The point is that the graph shows that we meet our thermal design goals if we choose a switching frequency of 330 kHz as recommended by the tool. Next, let's take a look at how to stabilize a design using the simulation tool. For this, we select the AC loop or Bode plot simulation from the toolbar on the right of the screen. The start frequency is 0.1 Hz. The stop frequency is 198 kHz. The input voltage is 24 volts. Source resistance is selected as 1 milliohm, and the output current is specified as 2 amps. Running this simulation shows a bandwidth of 36 kHz and a phase margin of 64 degrees. The tool designs for a crossover at 1/10 of the switching frequency, which is a conservative design and covers for most variations in the design. Let us now look at the time domain performance, for which we do a load step simulation. The input voltage, just to reiterate, is 24 volts. Source resistance is 1 milliohm. The start current for the load is 1 amp with a delay time of 1 millisecond. The rise time has been selected as 1 microsecond. The pulse current is 2 amps. The pulse width is 1.5 millisecond. And the fall time is 1 microsecond. The time domain response shows a damper first order response. The overshoot and undershoot are in the 3% range, which was the original goal of the design, which translates to about 150 millivolts. Let's say I'm not happy with the load transient response and want more design margin. I go in again and change my output capacitance to 2 times 22 microfarad, 1210 or 1210 case size, recognizing that the 1210 case size derates less, and I will therefore get more effective output capacitance. We recalculate, and the tool suggests a different set of values for the design, as highlighted by the red circle. We look at the Bode plot, and bandwidth is back to where it was, with a crossover of 37 kHz and a phase margin back to roughly 63 degrees. Now we run the load step response simulation again, and we now see a big improvement around 100 millivolts as far as the excursion is concerned. As you can see, the Maxim solution offers internal compensation while still retaining the flexibility of being able to recompensate the loop. In most internal compensation schemes on the market, you're stuck with a lower bandwidth, not with the Maxim device. Next, let's take a look at line transient. Line transient performance is important in applications where the input voltage has disturbances that you want to reject on your output. Current mode control implementation in the Maxim devices naturally lends itself to good line rejection. We will use the tool to examine this. Let's look at the design settings. Once again, the input voltage specifications are unchanged with a nominal input voltage or a start voltage of 24 volts, the pulse voltage of 32 volts, the delay time has been specified as 200 microseconds, the rise time of 1 microsecond, a pulse width has been highlighted of 500 microseconds, the source resistance remains unchanged, and the fall time is 1 microsecond. We hit run simulation, and as you can see, the switch node, which is the blue trace, shows the input voltage changing from 24 volts to 32 volts. The third pulse, in this case, is smaller than the first two. This is because current mode control's scheme uses the inductor current slope to determine each cycle's pulse width. The automatic reduction of pulse width is in response to the line voltage increase, hence limiting the disturbance on the output. Here's a visual of the output voltage disturbance of the line transient conditions that we just discussed. It's also easy to save and document your design for future reference. Comprehensive documentation is available, including design requirements, schematics, bill of material, and simulation results. While you can operate the ESIM simulation tool online on Maxim's website, users can also download the free version that can be used to run simulations on their computers in order to operate simulations that are perhaps not covered by the web tool. We suggest that you first run the basic simulation on the web tool and then download the schematic for your use. This gives you a good idea of the initial conditions populated. This is true especially for the Bode plot simulation. We encourage you to visit the Maxim site and play with this tool. We are confident you will like it. While we reviewed the Max 17503 as an example device, Maxim's Himalaya Synchronous Buck IC family offers a broad range both in the input voltage capability as well as the output current capability. The Himalaya series offers solutions which are optimized for 60 volt max operating voltage with an output current option from 25 milliamps all the way up to 5 amps with internal MOSFET devices and external MOSFET solutions for greater than 5 amp applications. We also offer a pin-to-pin compatible 42 volt or 4.5 to 42 volt max operating solutions, once again with solutions available for as low as 25 milliamps, as high as 5 amps with internal MOSFETs, and external FET controllers for requirements beyond 5 amps. All products are rated to operate over a wide minus 40 degrees C to plus 125 degrees C operating temperature range. All these products deliver the peak efficiency of greater than 90%. They require minimum number of external components to make an easy design for a quick time to market. And we offer pin-to-pin compatible voltage and current options to select depending on the nature of your application. Thank you for your time today, and I hope you enjoyed our talk on Maxim's Himalaya high efficiency DC to DC synchronous buck regulators. Thank you.